Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Hi, welcome to another episode of Driven. This episode's about LiDAR Perception. This is episode 20, and we're kind of winding our way towards understanding exactly how autonomous vehicle works. We're peeling away the layers of the onion in each of these informational episodes. And this one today is particularly near and dear to my heart because I've been working with these things called LiDAR for quite a while. But before we dive into that, just to kind of a reference to how this relates to more recent episodes, episode 19 on autonomous navigation, we talked about how an autonomous vehicle self-navigates, how it figures out, knows where it is and knows where it wants to go to next and knows how to steer the vehicle and, of course, accelerate and apply speed controls and steering controls to get it to the next waypoint along its route or path that it's set out and planned. So this episode really starts to dive into what happens when there's an object or an obstacle in the way of this self-navigating autonomous vehicle. If it didn't have any sort of sensors to detect that object, it would just plow right through it. And obviously we can't do that. That's not a good thing. And so there are cameras, as we've discussed before. There are radar sensors. There's ultrasonics. And then there's this thing called LiDAR, which stands for, I think it stands for light imaging and ranging, I believe, light detection and ranging, something like that. But it's LiDAR, and it's really a sensor that is pretty common and prevalent nowadays on autonomous vehicles that is LiDAR or laser based, I should say. It's emitting light or laser light out in front of the vehicle to detect, or to the sides of the vehicle, to detect what's out there, get a bounce back, a range measurement back that tells the sensor how far it is to something that is out there in the world that the beam bounced off of and reflected back. And in a nutshell, really, that's how LiDAR works. So, okay, we can call it an episode and wrap it up from there. But in reality, there's a little bit more to it. And LiDAR really... I first got exposed to them in terms of with respect to autonomous vehicles back in the 2005 DARPA Grand Challenge. I had a team, and there was a company called Team DAD. That was another team out there, and the gentleman behind that team had sort of created this one of the earliest incarnations of these rotating scanning LiDAR sensors that ultimately became the sensor that was sold by Velodyne, which is a popular LiDAR that has been used across a lot of different vehicles over the years. And but Team Dad was I think they were selling it for $250,000 or $300,000, something like that. But they made a special offer for the Grand Challenge teams of $150,000. I may have the math wrong. Maybe they were selling it for $75,000, but it was $75,000 to $150,000 sensor that some of the teams purchased and used. My team had a little bit lighter budget, so we opted for a LiDAR, a sensor from a company called SICK, S-I-C-K, that is a German-based company. That's the founder's last name, and but they do a lot of industrial sensing type applications, and they had a pretty popular LiDAR that was laser scanner, I guess you might call it, that would scan in sort of a two-dimensional plane. And this LiDAR from this company or from this group that ultimately became Velodyne, had multiple laser beams so that you can get what's called a point cloud. And we're going to dive into this in more detail in this episode. But suffice to say, these were pretty expensive back in the day. Now you can get that a laser, a LiDAR sensor that's about 1/10 the size, has maybe 10 times the range, maybe 5 times the range as what was available then at 1/20th the cost, right? Maybe even less. So we've come a long way since 2005, almost 20 years since that particular DARPA Grand Challenge, and the sensors have become smaller, giving you farther range, and many more range detection points, as we're going to talk about here, so that they're actually practically useful in these autonomous applications. But let's start with the most fundamental aspect of this is there, and has been around for a while, sensors that would emit light, or maybe even a laser level light, out into the world and get a reflection back. And based on sort of time of flight principles, where from the moment that beam goes out and the beam comes back, it knows, based on this constant speed of light, how far it traveled. And it's going to have to, of course, cut that time in half, because it's the time to go out, the time to come back. But this time of flight principle would give you this this distance measurement that would tell you how far it is to something that this laser beam reflected off of. And of course, it could be not sort of laser light. It can be sort of different frequency and frequency range. It might not be as precise. Of course, as this beam of light and or laser light goes out into the world, it's not just an infinitesimally small point. As it goes out farther and farther and farther, there's what's called a spot distance. The spot grows bigger, and so that spot, depending on how far it is and how precise this laser and or light beam is, might be picking up. It could be covering a very small point on an object or a very wide point, depending on the nature, the frequency of the beam. And of course, the less powerful the beam is, the wider this spot will be, and you'll get less accuracy, because you might be picking up other things in the environment before it hits the ultimate target that you're really are interested in, or vice versa. But of course, if it's too precise, and if it's a really high powered laser, you're going to shoot right through something, and that's not very good either. So that level of light is not that level of laser light is not obviously practical for autonomous vehicles. We don't want to be. This isn't Star Wars. We're not trying to destroy the world and destroy things in the physical world. We're just trying to know where things are in the world. So there's classes of laser light, and typically these are what I think we call class 1 lasers. There's also class 2, but class 1 is eye safe, and you're not going to get blinded, and you certainly know you're not going to have a laser beam shoot right through your body. But this kind of laser light can still be precise based on some physics principles and things that we won't go into detail here. Maybe in a future episode, we'll dive a little bit deeper in sort of the technology of LiDAR itself. But we want to talk about LiDAR perception, and suffice it to say that you get this range point to something out there. It tells you the distance to that object. Now, along came other companies, like I mentioned, SICK, and there's others out there that basically took this laser beam and have a rotating mirror inside, and would sort of basically take multiple measurements, maybe thousands of measurements, as that mirror is rotating very fast, and you're getting now a 2D scan of this laser in the environment, and you get a scan of points. And so now you might be able to pick up the shape of something that's out there just with sort of a singular line scan of this laser. As this mirror rotates, it's going to take hundreds and thousands of measurements as it's just sort of rotating around and getting measurement after measurement in the environment. So you get what I like to refer to as a scan of points, range points of something that's in the world, or a 2D LiDAR scan. And again, you can now sort of see sort of the shape of at least something. If you can imagine a human being standing out there, and that beam is sort of hitting them at their sort of stomach level, you're going to get sort of the width of someone's body, if you will, because you might have about, depending on how far out that person is, a couple points or hundreds of points that are sort of hitting the torso of that human being out in the world to detect how that they're there, that there's something out there. Of course, it might be a car or something else, and we'll talk about sort of the perception aspect of this. But there's these sort of 2D scan of points and those scanner type sensors. Then there's especially in the last, I want to say 10 or a little bit more years, they became those sort of three-dimensional LiDARs that I mentioned that Team Dad and then Velodyne had at the beginning of the show became more economical. And so now, instead of one laser beam scanning and getting one plane of information, companies would have 8 or 16 or 32 or 64 or 128 LiDARs, lasers, I should say, stacked on top of each other and all scanning and rotating. So now you had multiple line scans of what's out there in the world, and you really get effectively what we refer to as a point cloud, a cloud of points that represent the distance to things that these lasers are hitting in the world, and the range to those things out in the world. So you're now picking up everything that's out in front of the vehicle. You might actually have a LiDAR that has a 360-degree field of view. So it's just, if you have it on the roof, if you've popularly seen some of these vehicles that will have LiDAR scanners on the roof, they're scanning what's in front and on the sides and in the rear of the vehicle, because these beams are just kind of rotating in a 360-degree fashion. Also, there's some scanners that just will have like the forward-facing view, 180-degree, maybe forward field of view, 120-degree field of view. And it's not just now this scanning technology. There's kind of like this flash LiDAR type technology. It's almost like a camera image. These are solid state LiDAR type sensors. Instead of having the rotating mechanical mirror inside, they're sort of flashing the light, getting the range detections to things in a more instantaneous fashion, as they're sort of flashing these beams of light, almost like a camera in the environment. And typically, the horizontal field of view and the vertical field of view for these sensors is can be more limited, because it's just sort of looking out in front, and so you might get a 120-degree vertical sweep, maybe 90 degrees depending on the sensor, and or horizontal sweep, I should say, and then it might be 45. It could be 90 degrees on the vertical plane as well. But now you get sort of a grid of points that are coming out that represent what that LiDAR sees out in the world. And but regardless of whether it's a scanning LiDAR or or sort of this flash type LiDAR, you're getting this cloud of range points. And of course, the more lasers that you have, the more or the more flash points, if you will, that you have, the more resolution that you'll get coming into the sensor to tell you where things are in the environment. Of course, as the farther things are away from the sensor, you're going to get less resolution because the beams start to spread. And while you may get thousands of points for a human being that's standing close to a vehicle, you might only get a few for a human being that's standing out 50 to 100 meters, depending on the sensor. So, but there's this concept of a point cloud that come from these LiDAR sensors that now give you this this perfect sort of sense of really what's out there. These are magnificent images of objects that are of the things that it hits in the world, and you get these really crisp pictures of trees and cars and signs and people and whatever's out there in the world. And you can liken it to, if you've ever seen these toys where you have these needles that sort of stick out, and then you put your hand into the object or your face into this object, and the little pins sort of create this shape of your face or the shape of your hand. And in some ways, I kind of visualize and think of these point clouds and the LiDAR data that you get is similar to that, because it is in this case of these toys that give you this shape of your face, the shape of your hand, or whatever you're putting it over. It's telling you the relative distance in many ways to those things if you measure just how far out those needles are protruding from what it was touching. So in this case, with the LiDAR point cloud, you're getting these range points for all of these things out in the world that these LiDAR emissions are detecting. So as you can imagine, with any kind of sensing application, you have to do filtering of some sort of noise, environmental noise. You can get noise in the information that you're getting back from these sensors, in the sense that they may be, there might be rain, right? And so the rain is effectively noise. You want to filter out if these LiDAR sensors, hit a raindrop, which they can do, or snow, snowflakes. They can give you reflections back, and so you'll see, you might be getting the shape of some object, but then a bunch of spikes that come out because it's hit these raindrops or these snowflakes before it hit the actual object. So you get back these reflections, and we consider that environmental noise. And there are some LiDAR sensors nowadays that have what's called like a multi-pulse technology, where they're sending out multiple pulses, maybe again in different. There's different sort of physical ways that they do this, but multiple pulses for one reading. And if it hits while it might hit the raindrop on one of the pulses, it might, after a subsequent pulse, it might hit something farther out, or vice versa. It might hit something farther out first, and then the raindrop on the second pulse. So it might be 2 pulses, 4 pulses, if they have this kind of technology. And so you can get multiple readings back, or just you can sort of tell the sensor, just give me the farthest thing it hit, because you know that if it hits something sooner, that's going to be presumably a raindrop or snow, and so you want to get the farthest thing that it hit. You can of course ask for the first thing it hit, and there's other ways to configure these sensors, but that's one way that noise filtering can be accomplished within the LiDAR sensor itself. But of course, AV software developers, such as ourselves, will write. We have algorithms and ways to kind of detect these noise spikes and know, well, this is unusual because we had this really flat surface, and now all of a sudden there's this one singular point out there in the world that's sticking out. So we can just filter that out, maybe interpolate the fact that is a noisy point in the world. There's also noise that comes in the form of that spot distance that I mentioned. As that beam goes out, again, you're not getting this pinpoint precise measurement necessarily. You might think of it as that, since it's a laser, and lasers make you think of pinpoint precise measurements, and it is as precise as pretty much anything else out there. But you can still have this spot distance where the beam will kind of widen as it's shooting out, and and part of that beam might pick up a tree leaf or something before the rest of the beam hits a car, and or something else out there, and you might consider that noise. But there's also this concept of a ghost point, where some of the sensors will, depending on the energy, how it calculates the range to something, it might say, well, if half of that spot hit that tree limb and half of the spot hit a car further out, it might take the average. So it might give you a range point that's sort of halfway between the distance between that tree limb and that car. And that's real, but that's really not a real point in the world. It's just, we call it a ghost point because it's kind of fictional. But it represents sort of what the sensor is able to infer based on the energy reading that it's getting back, because of that spot distance. So there's noise in that sense as well that you may need to filter out. You may need to filter out these ghosty points when you're looking for a really precise sense of what's out there in the world. So given what these sensors are capable of doing, let's just talk briefly about how do you infer what an object is with, let's just take a 2D scan, a single line, a single beam that's going out there, where you might have multiple points hitting the cross section of someone's torso, as I mentioned, or say, let's just imagine a box for simplicity. There's a box out there, and the scanner is scanning, and it's going out into infinity, or maybe it's hitting something way out there, way down the road. And then all of a sudden, now some of the laser points are reflecting off of a box that's about 10 meters away. So now you might get, depending on how wide the box is, let's say, 10, 100 points coming back from that box. And now then after that box sort of ends, or you get to the end of that box with the scan, now the beam's going to go out much farther. So one sort of simple method for inferring that there's an object out there is to look at these the differences between as you go through these points and see, okay, the current point that I'm looking at is 50 meters out there, and now there's a point that's 10 meters away, and now there's a successive sequence of points that are all about 10 meters away, and then all of a sudden now there's another point that I'm getting that's 50 meters away. So that difference between sort of creates this, you can imagine sort of this bump in the world, this if you're visualizing what this 2D scan looks like, you can say, okay, if there's a difference of a meter or 2 meters or whatever it may be, that clearly that's some protrusion in the world that I should be interested in, and maybe considering that there's an object out there. Now there are other algorithms, many algorithms for doing this, and there's neural networks and ways to train, and we'll cover that in an episode as well. Some of our machine learning episodes that are upcoming, about how to train these systems to perceive objects in the environment based on these sort of patterns that can be recognized. But in the simplest case, you can think of LiDAR perception and detection of in this case objects with these 2D scans as looking for these bumps in the world, these protrusions in the space that you can sort of say, well, that's clearly an object. You can also look for dents, if you if you want to think of it like that, in the space. If these LiDARs are looking down on the ground out ahead of a vehicle, and you see sort of a dent, you might consider that a cliff or a ditch or something that you want to avoid, a negative obstacle or a negative object or obstacle, as we might refer to it in this case. So that's 2D LiDAR. Now you can extrapolate this to the third dimension when you think about multiple laser beams sort of scanning and rotating and getting that 3D point cloud that I referred to. That same algorithm can be applied to each layer or each slice, if you want to think of it like that. And then you could stack the objects that are detected like slices of bread to build up a loaf of bread, and know that, okay, this is some volumetric object out there in the world that not only has some width, but has some height to it, because 4 of my 128 laser beams that are stacked vertically, one on top of the other, are now detecting something that's out there in the physical world. And but there are other algorithms and other ways to kind of look for objects, not just by virtue of that sort of scanning methodology in the 2D sense, but you can actually start to, as you're scanning each point, look at the next layer above and the next layer below, and also get some additional information to know if that point that you're looking at as you're sort of processing this data is actually part of an object, or if it's again noise or something like that. But suffice it to say that with these methodologies, various ones that do exist, you're getting this volumetric sort of protrusion in the 3D world from this point cloud that tells you that there's a car out there or a person. And because it's these point clouds give you more data in sort of in these different dimensions, and you're not just getting a singular scan of someone's torso. Now you're getting, say, 100 scans of the human. You can actually see the shape of a person out there, or the shape of a car. And based on these shapes, you can actually start to classify things, because now while if you just had a 2D LiDAR, you're getting a scan of something, you see a dent in the world. It could be a car. It could be a couple of human beings standing next to each other. But as you get these sort of a fuller picture via the point cloud of what's out there in this world, you can infer shape and say, okay, this is actually a car. You can classify and say, this is a car, this is a human being, this is a person on a bike, this is a pelican, this is a dog, this is a street sign. So you can these 3D point clouds and this methodology of looking for these protrusions in 3D space are the methods by which we perceive, using this LiDAR data, that there are objects out there that we need to be concerned about or aware of as our vehicle is navigating down the road. So we talked about 2D and 3D, but I like to think of detecting objects in 4D as well. And in this case, we're just referring to time. And this sort of gets into fusion as well. You're going to be detecting from one scan of the LiDAR, say, a car that's out there in the world, and then from a subsequent scan at time t1, you're getting another sort of point collection of points that are protruding in 3D space that represent that same car that may have moved a little bit. At time t2, now you're getting another scan. The car's moved a little further. Keep going, time t4, and you can sort of build confidence that actually your scan is actually a scan of something that you should be concerned about out there in the world, and maybe also start to calculate its direction and its speed, because you're looking at the change now in distance of these objects over the change in time. So change in distance over change in time is speed. So you can get the speed of the objects and the trajectory of them. Where are they going? Are they coming at you? Are they going away from you? Are they traveling at 10 miles an hour, 55 miles an hour? All that kind of information can now be gathered as you look at the detected objects and the scans from this LiDAR over time. And again, this starts to get into what's called sensor fusion as well, because you can look at the fused data from multiple objects and really infer this kind of information as well based on the fusion of data. But just looking at the data from one sensor for the purposes of this discussion over time, you can get this kind of extra information from LiDAR and its perception capabilities. And again, going back to filtering out noise or filtering out things, maybe at time t0 you detect something that's right in front of the vehicle. Maybe it's a leaf or the flap of a box that's sort of floating around in the wind, a tumbleweed or something. And then at time t1, it's not there, or it's it's gotten smaller or something like that. And time t2 comes along and you haven't seen it again. You might say, well, that was just a blip in the matrix, if you will. That's something that I don't have to necessarily be concerned about, or I lower the confidence of my need to be concerned about this thing that I saw that was probably just a leaf, because now I haven't seen it multiple times. Of course, the size of the object may factor into your confidence and how you want to react to things, but you certainly might want to react to things as small as cats and dogs and certainly small children that are in the environment, but maybe leaves and things that are smaller aren't of concern, but maybe rocks are. So size isn't always the important factor there. You might want to consider other facets of the data that you're getting to determine and infer whether or not you have to react to that. So that's a little bit different from perception, because perception is really just taking the data, in this case from the LiDAR, and determining whether or not it is an object. How you react to that is sort of a different facet of object detection and avoidance. We're talking about object detection. Then there's object avoidance, object detection and avoidance, right? You might hear of ODA or ODOA, that term. And this is really about OD, object detection or perception. Now, it's very common in autonomous vehicles. The LiDAR is going to be in the front of the vehicle or on the sides of the vehicle, of course, behind the vehicle. And it's projecting outwards. And if you have sort of a smooth, flat road ahead of you, these beams are going to obviously hit the ground and hit the road. And if you're looking longitudinally along the path of the vehicle in front of you, you'll get this scan of the road ahead, and you'll see that you have all these points that indicate that there's a flat road ahead. If there's a person or a car out there, suddenly now these points are going to jump up in height in the z-axis and tell you, okay, now there's a difference in these points, and they're clearly hitting something out there that's a sudden jump up, and that's not the road. That's something to be concerned about. And then, of course, as it looks over that person or what have you, if the road is if you've got a hill ahead of you, right, or the road's kind of curving upwards as you're going upwards in altitude, if you will, along the highway, that road still may give you sort of a smooth surface and tell you that that's still just road ahead and not an object, because typically you're not going to have a sudden jump in the road that you do with an object like a person or a car. You're going to have a more gradual sort of smooth rise. And so that gradient, that changing gradient in the Z direction as you're looking out, looking at the point cloud data, is something that you use to do what we call, at least we call it, ground plane discrimination. You want to kind of know that because you might be looking out very far with some of these LiDARs, and you want to know that that's just the road out there, and that's not somebody necessarily, or some car that's out there in the horizon. Now, there is wet ground, and wet ground can sometimes, wet pavement can sometimes lead to non-reflective surfaces. And you might actually, for very close to the vehicle, especially as the beams are looking straight down, or if it's sort of reflective out ahead of the vehicle, because it's fresh rain and there's like a slick road ahead. The beams may the reflections that you get may be a little befuddling. You may not see anything. It may give you it may look like it's just some sort of infinite ditch in the world ahead of you. So you kind of have to look at that information and say, well, okay, this is, there's not a sinkhole in front of me. I know from other sensor data, and this is where fusion comes in, that that's not a sinkhole. But when you look at this LiDAR data, you may get infinite reflections or information from the sensor that makes it looks like you're looking into infinity, into space, and but that's the road ahead because of some of the points that led up to that infinite reflection, as I refer to it, and then the points that are immediately after that. And of course, as you're driving along, that 4D concept of information over time tells you that there was something there just a second ago, and that hole didn't just magically appear in front of the Earth. But you can get this kind of noisy or befuddling information from a wet ground as it's currently raining, or even if it's stopped raining and the road is wet, and the pavement just doesn't give you any give the LiDAR reflections in certain points along the road ahead. So ground plane discrimination, and also and algorithms to figure out what is the ground, is there a ground, is very important, because you want to avoid false detections that are going to make the vehicle suddenly stop incorrectly. But you also want to be able to know that there's a gradual slope ahead versus an actual object, so that you're not unjustly slowing the vehicle down in some sort of odd, potentially also unsafe fashion. Now, with every LiDAR, there's this concept of reflectivity, or with most LiDAR, I should say, where you can also, for each beam, not just get the distance to an object, but it can tell you how reflective that object was. If it's a white surface, it's going to be more reflective. If it's matte black, it's going to be less reflective, right? So you'll get a reflectivity value. Let's say the most reflective is 1, and the least reflective is 0. And so there might be some normalized value between 1 and 0, might be between 0 to 100 or what have you. But this can come in handy if you want to look for lane lines in the road ahead, because there'll typically be a black paved road, and the lane lines by definition are going to be yellow or white and are going to stand out and be more reflective. So as this laser is looking out ahead on the road ahead, you can actually get reflectivity values. It might be the same range to something, the ground, because these lane lines are right on the ground, but they might have a reflectivity value that can tell you that that's a lane line, and that can come in handy for lane keeping, lane detection type algorithms. So there's some value that comes from LiDAR, and it's being able to tell you how reflective something is. That these range points, these laser points, are hitting out in the world, and you can get some additional information from that. It can't tell you the color like a camera can, but it can tell you how reflective something is. And last, but certainly not least, important consideration is how far can these lasers, these LiDARs see? And that's going to vary based on the make and model. But typically you'll see range values that say at 10%, and this is important, at 10% reflectivity, you can see out, X meters, let's say 50 meters. And so what that's saying is something that's 10% reflective, like something that might be matte black, this laser is spec to see it out at 50 meters. And something that's 90% reflective, like something that's very, bright white, you might be able to see out 100 meters, right? See that thing out 100 meters, but just be able to see that matte black surface on the car, say, or dark blue, at that, maybe it's 10% or 15% reflective, at 50 meters. So that range specification is particularly important. And you want to look for that 10% range reflectivity value, because, there's a lot of vehicles out there that are not shiny and new, and just have different reflectivity properties. But so you want to kind of design your autonomous vehicle solution to kind of look for that 10% range, or be aware that that 10% range is about as far as you're going to be able to see. Then there's also what's its minimum distance that it can see. A lot of sensors have a blind spot for, say, it could be up to the first meter. It could be, depending on the sensor, it could be the first foot or so. But so anything closer than a foot or closer than a meter won't be detected. It'll block the field of view, so you'll see what's called like a shadow, right? Because there's just this infinite reflectivity that might, infinite set of points that might say that, I can't see anything, but it's not really detecting the range to that person or that whatever it is, car that's within a meter away from the sensor, depending on what the spec is for that. So that comes into play with how you architect and design where the placement of sensors. You're not just going to put one LiDAR necessarily on the vehicle. You might be putting multiple. You might have the top hat, the one on the roof, and so you don't have to really worry about that as much, because it's always going to hit something beyond a meter that's away from the vehicle in that case, typically. But so there's a minimum range distance, minimum detection range. Then there's sort of the maximum range. And again, that's going to widely, vary depending on the sensor that's selected. It could be a sensor that's only capable of seeing out to 35 meters with 10% reflectivity. It might be spec'd at 100 meters. We're now seeing ones that have 200 meters. There are higher end ones that can see 300, 400, 500. They get more expensive the farther out that you look, and or spec'd to look. And but also then the field of view can start to get limited. So now you need more of them, right? So there's a whole discussion of LiDAR architecture that we could talk about in an upcoming episode. But that range factor is obviously going to be important with what you're actually able to perceive in the world, ahead of the vehicle and on the side of the vehicle and behind the vehicle. So that's LiDAR perception in a nutshell. There's a lot more that we can talk about with regards to algorithms, as I mentioned, like machine learning and pattern recognition for different perception algorithms and different ways to do perception. But at the end of the day, hopefully this gives you an idea that you're really looking for sort of bumps in the world that come from this range data from this highly resolute LiDAR detection capability. So thanks very much. Hope you enjoyed this episode of LiDAR Perception, episode 20 of Driven. See you next time. I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web, and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.